right. On to a new chapter. Chapter 3. The derivative formulas. A lot of people actually really like this section. At least relatively speaking. So if you don't like graphs, if you're tired of talking about graphs, you're like, stop talking about graphs. I get it already. All right, well, I got some formulas for you. How about we do some formulas instead? Would you like to do that? Yeah, so let's learn. I could say more about it, but let's just do it. Let's get into it. You can do this. No problem. Oh gosh, there's a graph on the first slide. Oh, I lied. Okay, I couldn't help myself. All right, so look, we gotta remember what the derivative means. Derivative f prime of x. What does that mean again? That means that's the slope of the graph of f of x. Okay, represents the slope. All right. So for a constant function, if you have a function that's just a number, just some number, no x, then the slope is 0. This is what the graph looks like. This is a horizontal line. Horizontal lines have slope 0. 0. Difference between any two y values will be 0. Okay. Remember that rule. Any number that I could put hidden here at all. I use -5. I could choose 11. I could choose 112. I could choose negative 1.4545452. It doesn't matter. Any number, no x, derivative is 0. Got it? Okay, good. Let's learn the next rule. For a linear function, y equals mx plus b. I like to use that form for linear functions. It's pretty conventional. All right, then we have the slope, or the I'm going to stop using the word slope. The derivative is the slope of the line. Okay, the derivative is just m. All right, so if you have a function and it looks like mx plus b, whatever that m is, that's the derivative. That's the derivative. All right, so here's the function. Here's what it looks like. Whatever that slope is, that's the derivative. Okay, so far so good. So far so good. Now's where the fun begins. Now is where, okay, we need to think a little bit sometimes. Not really think, just make sure we understand how to apply this next rule. This is called the power rule. This is the most common rule that you will use the whole semester. It's probably the most common rule for taking derivatives. It applies to the greatest number of functions that you'll see, I guess. It has a lot of applications, but it only works if you can write the function as in the form of x to some power. All right, so x to some power. That would apply to x squared, x to the 10th, x to the negative 10th, anything like that, x to the 1/2, and so forth. All right, the way you take the derivative, here's the formula for the derivative. That exponent, it comes out in front, and then you subtract 1 from the original exponent. So the derivative of x to the a is a times x to the a minus 1. All right, so that's that. Now, let's look at some examples, because there's a lot of flavors that this rule comes in. So the cost function, for example, let's say the cost function is given by q to the 43rd. All right, seems strange, but let's suppose that that's the function. All right, well, can we apply this rule to that? Yeah, it's of the form x to the a. X is q in this case, right? All right, no problem. So we'll just bring that 43 down out in front, and we will subtract 1 from the original exponent, 43. So we now have a 42 there. Easy enough? Let's look at another example. H of t equals square root t. Can I apply this rule? Is this of the form x to the a? It doesn't look like it, does it? Okay, but can we write the square root of t as t to some power? And the answer is yes, we can. We can write it as to the 1/2 power. Remember, square roots are, that means to the 1/2 power. Means the 1/2 power. So square root t, that's t to the 1/2. And now I can apply my rule. I can apply my rule. That exponent comes out in front. So that 1/2 here comes out in front. And then we subtract 1 from the original exponent. So instead of 1/2, we have 1/2 minus 1, which is negative 1/2. All right. Good. Let's look at another example. Let's say we have the function is 1 over x to the 9th. Now this is almost of the form that we could use it, but is it quite of the form x to the a? It's of the form 1 over x to the a. That's not quite of the form, but how can we write this of the form x to the a? Can I write it as x to the minus 9th? And the answer is yes, I can. 1 over x to the 9th, that is 1 over x to the 9th is x to the minus 9th. Whenever you change the sign of an exponent, it flips the fraction. Reciprocates it. Okay? So x to the minus 9, is this of the form x to the a? The answer is yes, it is. A is minus 9 in this case, so that minus 9, it comes out in front. And then we subtract 1 from that exponent. Minus 9 minus 1 is minus 10. All right, not minus 8, but minus 10. Okay. All right, so that's the basic gist of the power rule. So I hope that made sense. You will get lots of practice on the homework for applying the power rule. Now we need to talk about what happens if you know how to take the derivative of each piece of a function, but they're being added together. Right? We have a sum of two functions, and let's say you know how to take the derivative of each piece. Then what's the derivative of the function overall? It's just what you would expect. It's exactly what you would expect. It's just the sum of the derivatives. The derivative of the sum is the sum of the derivatives. This is very common math language, just to talk like that. All right. So let's see an example. Let's say we have f of x equals x to the 3.14 plus x to the negative 11. All right. Well, I know how to take the derivative of x to the 3.14. That 3.14 is just going to come out in front, right? Yes. And then I'm going to subtract 1 from the 3.14, right? Yes. I also know how to take the derivative of x to the minus 11. The minus 11 comes out front, and then I subtract 1. Minus 11 will become minus 12. All right. So what I will do then is just add those two things together. All right. So I do the derivative of this one, and then I add it to the derivative of this one. Okay, because the original functions were added together. Just as you would expect. Just as you would expect. Now this also means that you could have many functions added together, and if you know, as long as you know how to take the derivative of each one, like when I say functions, I'm thinking of like t to the 5th as being its own function, right? I know how to take the derivative of that. Oh my gosh, why did I write q? This should be a t here. This should be a t. Imagine that's a t. All right, don't look at it. It's a t. All right, so t to the 5th. So we have a sum of a bunch of functions, and we can apply the power rule to all these. Right? Now the derivative of t to the 5th. That's 5t to the 4th. The derivative of t to the 4th. It's 4t to the 3rd. Derivative of t to the 3rd is 3t to the 2nd. Derivative of t squared is 2t to the 1st, which we will just write as 2t. The derivative of t, now we're thinking of this as we can think of this in two different ways. We can think of it as in terms of that second slide, I think, that second formula that I gave for a linear function. If you think of this as a linear function, what would the slope be? The slope would be 1, the number out in front of t, right? And so the slope is just, so the derivative is just 1. So the derivative of t is just 1. You could also use the power rule. So t is t to the 1st power, and if I think of that 1 as coming out in front, well, it's still 1 times t. And then if I subtract 1 from that exponent, it's now t to the 0. T to the 0 is 1. So I have 1 times 1 is just 1. All right, so two different ways to take the derivative of t, but it's just the derivative is 1. All right, how about the derivative of 1? Derivative of 1, does that depend on t? Or is that just a constant number? Because if it's a constant function, then the derivative is just 0, right? And if the derivative is 0, I'm just adding 0 down here. I don't need to write that, do I? Because anything plus 0 is just the anything, right? Doesn't change it. So the derivative of t is 1. The derivative of 1 is 0. We don't write that. The derivative of t to the minus 1 is minus t to the minus 2. And the derivative of t to the minus 2 is minus t to the minus 3. All right, so that's how you would do that. Okay, good. Good. T's, not Q's. Okay, let's move on. Now we have a very similar rule here that what if I know how to take the derivative of a function, but it's being multiplied by some number? What do I do with that number? Well, I just kind of carry it down. All right? It just as this is another rule where it's just as you would expect. Now there are some rules that we're going to talk about soon, like the chain rule and quotient rule. I actually think that Mrs. Boardman is going to be talking about that, but those are not as easy as this rule here. All right, so let's see an example. If we have 5x to the third, now I know how to take the derivative of x to the third. That's 3x to the second. That 3 comes out in front, and I subtract 1 from the 3. So 3x to the second. So how does this 5 change things? We just multiply that number that comes out in front. That this 3 is going to come out in front. We're just going to multiply that by that 5. Okay? So the derivative of x to the third, that's this 3x squared. And that 3 will just get multiplied by the 15, by the 5 to be 15. All right? Have another example here. We have a sum of functions, and so let's just focus on each piece. So 3t to the 9th, that 9 will come out in front, multiply by this 3, and then I'll be left with t to the 8th. So 9 times 3 is 27, t to the 8th. This 6 will come out in front, multiply by the 4, and then I'll subtract 1, and then I get t to the 5th. And then how about 8 times the square root of t? Well, remember, we can think of t square root of t as t to the 1/2 power. So that 1/2 will come out in front and multiply by the 8. What's 1/2 times 8? 4. And I had t to the 1/2 here, right? When I subtract 1 from 1/2, I get negative 1/2. Negative 1/2. All right, so that's an example of how you do that. Good. All right, now, easy part. After you found the derivative, you can just plug in values of x. All right. So, for example, let's say you have this function here, easier than many of these other examples that we've looked at so far. X squared minus 7x to the third. So we'll take the derivative. So if we want to find this, what does this mean? F prime of 5, that's the derivative when x is 5. Right, exactly how it looks. So we'll take the derivative first. So derivative of x squared, that's 2x. Derivative of minus 7x to the third, that's minus 21x squared. And then we'll simply plug in x equals 5. So I'll just plug in 5 there for x, everywhere I see an x. And so I have 2 times 5, minus 21 times 5 squared, and that's 10 minus 5, 25, which is negative 515. Easy as that. All right, let's look at an applied example. So we have the cost function to produce q items. And let's say the cost function is given by this formula here. And let's say we're asked to find c prime of 50. All right, well, we're going to do it the same way we did the previous function, but the main difference is that we're going to have units. We're going to have units. See, 515 we didn't have units because it was just f of x. What is f of x measured in? It's just a function with numbers. Okay, so let's find the derivative of this function first. What's the derivative of 500? Well, that is 0 because that is just a constant function, right? Just a constant. So it goes away. What's the derivative of 20q? That would be 20. And what's the derivative of q squared? That is 2q. That's 2q. And then we'll simply plug in 50 for q. So I'll evaluate this at 50 by just plugging in a 50 wherever I see a q, which was only in one place. And what I got when I did that was 120. And what is that measured in? Remember, the derivative, that's like the slope. So the units is the same as the units for slope. So it's dollars per item. You could put a dollar symbol here if you don't want to write out dollars, but you need the per item there. Per item. Okay, so that's that. We started talking about the second derivative 2 times ago, and yeah, you can do that here. And it's pretty straightforward, just as you would expect it. Works just as you would expect it to work. So we usually, of course there's a third derivative, fourth derivative, and so forth, but, at some point it becomes kind of a reach in terms of like what it would mean to talk about like the 20th derivative or something like that. So normally we just stop at the second derivative because we can kind of grasp what that means a little easier. So let's say we have this function here and we want to find the second derivative. Well, first you would write the first derivative, right? So the derivative of x to the third, that's 3x squared. The derivative of negative 5x squared, that's minus 10x. That 2 comes out in front. And after we subtract 1, we just have negative 10 times x to the first, which we don't have to write to the first power. Then the derivative of x to the 1/2, that 1/2 comes out in front. X to the minus 1/2, because 1/2 minus 1 is negative 1/2. And the derivative of 7 is 0. Okay. So we got the first derivative. So if we wanted the second derivative, we would just take the derivative again. Just do the same thing, same process. All right, so this exponent comes out in front. We have 6, x to the first now. Negative 10, x to the first. Imagine there's a 1 up here. The 1 comes out in front. And then it's to the 0 power, and 0, anything to the 0 is 1. So anyways, the slope of negative 10x is negative 10. And on this one, you also just bring the exponent out in front. You have a 1/2 already out in front, and when we multiply it by negative 1/2, remember how multiplication of fractions work, that we just multiply straight across. So 1 times 1 and 2 times 2, that's a fourth. We have 1 negative sign, so it's a negative. And negative 1/2 minus 1 is negative 3/2. Remember, you need to get a common denominator before you subtract fractions like that. Okay. All right. So that's that. So that's the second derivative. And graphs. Said that we were going to take a break from graphs. Such a liar. Such a liar. Okay. Remember how we first talked about the derivative as being the slope of the tangent line at a particular point on the graph. All right, so let's say we had this function here, negative x squared plus 2. Then what's the derivative? Well, we use the power rule, and this 2 comes out in front, and we have minus 2x to the first power. This just goes away because it's a constant part, and derivative of constants are 0. So the derivative is negative 2x. Okay. So what would the derivative at 0 mean? Well, when I plug in x equals 0, I have negative 2 times 0. Anything times 0 is 0. So I have 0. All right. Well, here's the graph of the function. And if I make the tangent line at x equals 0, I get a horizontal line. And horizontal lines have slope 0, 0. Right, so that's what we have found. All right. How about f prime of 1? Well, here's my f prime. When I plug in 1, I have negative 2 times 1, which is negative 2. All right. So let's see. Does that make sense? Well, we have the graph of the function here, and at x equals, it's a little bit different window, so the graph looks a little bit different. But at 1, we have the function right here, and if I draw the tangent line, this yellow line here, coming off the curve, then what's the slope of that line? The slope of that line is -2. That's what we have found. All right. So all this calculating derivative stuff, that's finding the slope of the tangent line at that point on the graph. All right. So, good. So that's that. All right. Now, notice that the slope of the tangent line. So what have I said here? Notice that the slope of the tangent line is x equals 0 because I already. This is just for you to read. I already said it out in words. But yeah, that's what we found. All right. Well, that is all I have for you today. I think we covered everything. Good luck on your Widely Plus and stuff. And yeah, we'll see you next time. All right. Have a good one. Goodbye.